Hey, this is Horner. We're going to look at the 17.1 and 17.2 solutions to the problems that you needed to do. For this first one, it says that in each of 5 situations, you have 2-point charges. So here are the 2 charges in each one of the situations, and they're separated by a distance, and they give you that distance for each one. They want us to rank the order of electric potential energy from highest to lowest. So really all we need to do here is just use our potential energy due to the electric force. So that's equal to K times Q1 times Q2 all over R. Notice that it's not R squared. If it was R squared, it would be force, but now we've switched and we're just looking at potential energy. So let's do the first one. For letter A, we have 1 times 2 over 1, so that one's 2. For letter B, we have 3, we have 2, it's my fault, we have 2 times negative 1, and that's divided by 1. Getting ahead of myself here. And that one is equal to negative 2. For letter C, here we'll make that a 1, we have 2 times negative 4 over 2, and so this one's equal to negative 4. For letter D, we have negative 2 times negative 2 all over 2, and so that's a positive 2. And then finally for letter E, we have 4 times negative 2 all over 4, and so we end up with negative 2. So to rank these from highest to lowest, we would have A is equal to D, because those are both 2's. That would be greater than B, which is equal to E, because those are both negative 2's. And then finally, that is greater than C. That is the first problem. So let's go ahead and take a look at the next one. Next one is number 3. It says a hydrogen atom has a single proton at its center and a single electron at a distance of approximately 0.0529 nanometers from the proton. They want us to find the electric potential energy in joules, and then they want to know what is the significance of the sign of the answer. Our potential energy is equal to K times Q1, Q2, all over R squared. We know that K is about 9 times 10 to the 9th. For a proton, we have 1.602 times 10 to the negative 19th coulombs. And then for an electron, it's the same thing, but negative 1.602 times 10 to the negative 19th coulombs. And we can divide that then by 0.0529 times 10 to the negative 9th, because nano means times 10 to the negative 9th. If you plug all that into your calculator, you should end up with negative 4.36 times 10 to the negative 18th joules. And they want to know what is the significance of the sign of the answer. So when it's negative, what does that mean? That negative sign just signifies that the force between the 2 charges, so we know that the force of electricity between the 2 charges is attractive. So they do attract each other. And the potential energy is lower than if the 2 are separated by a great distance. So it's got a very small, very negative potential energy because of that. For number 4, this one says how much work is done by an applied force that moves 2 charges of 6.5 microcoulombs that are initially very far apart to a distance of 4.5 centimeters apart. For this one, we're going to just say work is equal to the potential energy. And so that's equal to K times Q1, Q2, all over R. And for this one, we'll go ahead and put in our 9 times 10 to the 9th. And then our charges are both 6.5, and then remember micro means times 10 to the negative 6 coulombs. And we're going to square that because the 2 charges have the same charge. And we can divide it by the distance between them, which is 0.045. And so we end up with 8.4 joules. All right, let's take a look at number 7. This is one that deals with biology. So we have a hydrogen bond in a DNA molecule, and that hydrogen bond is actually an electrostatic interaction of 4-point charges along a straight line. So they want us to estimate the energy that must be supplied to break this bond. In order to do this one, we just need to find out what is the total energy there for the bond. And for that, we're going to look at the sum of all of the energies. So K times Q1 times Q2 all over R between 1 and 2. And so we can pick any of these to be 1 and 2, and we can do those as we go through. So let's do this. Let's just number these. 1, we're going to do 2, we're going to do 3, and 4. And we want to look at the interactions, and notice this is just a generic equation, so don't take to heart these 1s and 2s as just being this and this. It could be the first and the second one, so it could be 1 and 3, and then it could be 1 and 4, and then 2 and 3, and 2 and 4, and that's essentially what we're going to look at. So this is going to be equal to, now notice K, we can take that out, that is 9 times 10 to the 9th. And everything else we're going to leave inside except for, notice they've put E here, and E is 1.602 times 10 to the negative 19th. So we're going to take both of those things out to make this a little bit easier. And then on the bottom, because the radius is in nanometers, we're going to put that on the bottom here. We're just going to go ahead and put 10 to the negative 9th. So now when we do the rest of this, we can just use the numbers that they gave us. So we need to look at the interaction between 1 and 3, because here's the hydrogen bond. So between 1 and 3, we have a negative 0.3 times negative 0.4 charge. And the distance between the 1 and the 3 here should be 0.3. We're going to take that and add it to, now let's go ahead and look at 1 and 4. So this is going to be negative 0.3 times 0.4. And then the distance between those is going to, looks like that one is 0.42. So we'll put that one down. So this is 0.42 plus, and then we're going to do the next one, which is going to be between 2 and 3. So 2 is positive, we'll go and put positive 0.3 times negative 0.4, and we're going to divide that one by 0.18 because that's the distance between them. And then the last one is going to be between 2 and 4, and so that's going to be 0.3 again times positive 0.4, and the distance between those is also 0.3. So now if you add all these together, okay, and you're going to need to, I would go ahead and just divide this through, divide this one through, divide this one through, and divide this one through, so you don't have to come up with a common denominator. Once you do that, then multiply whatever your answer is times what's on top, and divide everything by 10 to the negative 9th. And when you're done, you should end up with 4 times 10 to the negative 20th. And remember, this is energy, so it is measured in joules. And that is the end of number 7. So it looks like a really tough problem. It's really not. We're just going to go through and think about where that bond is and then how things on the opposite side of the bond will attract each other or repel, depending on what they're doing. For the next problem, this is number 13. We have in the diagram, they want to know how much work is done by the electric field as a third charge, and so we'll call that third charge Q3, is moved from infinity to point A. So we're going to move this positive 2 nanocoulomb charge to point A from infinity. So when we do that, we want to compute the work done by the electric field. The work done by that electric field is going to be equal to negative times the change in the energy. And so we really just want to know what is my original energy, and we're going to subtract my final energy from that. And so in order to look at that, we need to look at the energy between number 1 and 2. And we're going to subtract from that then the energy of 1 and 2 plus the energy between 1 and 3 and the energy between 2 and 3. So if we go through and we do some math, we'll end up seeing that this is really then just the negative energy between 1 and 3 minus the energy between 2 and 3. Okay, so let's go ahead and put in our equation. Our equation here is negative K, Q1, Q3, over r, and that's between 1 and 3, minus, and then we've got k, q2, q3, all over the distance between 2 and 3. Now we can go ahead and plug our numbers in. We can factor out a k, and that k is, let's factor out the negative too. So negative, and then we have 9 times 10 to the 9th. And we're going to multiply that times 2 times 10 to the negative 9th. So that's our charge in question. And then we've got 8 times 10 to the negative 9th over, and then we have 0.04 meters, plus negative 8 times 10 to the negative 9th over, and then we've got to add some distances together, so we've got 0.04 plus 0.12. And when we're done, we're going to end up with negative 2.7 times 10 to the negative 6th joules, or negative 2.7 times 10 to the 6th microjoules. And I just want to make a really clear note here. You might be confused as to where this came from, and really all we did is we just took, you have U12 minus U12, so those go away, but then you still have negative U13 and negative U23, so that's why you see those here. That's what you end up with. So no, didn't want you to have any questions about what's going on there. Just wanted to make sure that you saw that. For the next problem, it is number 17. It says a point charge of 3 nanocoulombs moves through a potential difference of 25 volts. They want to know what is the change in electric potential energy. So here the change in electric potential energy is just equal to the charge times the change in potential. And we have 3 nanocoulombs. And we have 25 volts. So this is really 3 times 10 negative 9th coulombs times 25 volts. So you're going to end up with 75 nanojoules, or that's really just 75 times 10 to the negative 9th joules. And that's all there is to number 17. For number 19, it says find the electric field and the potential at the center of a square of sides 2 centimeters. So we have all these are 2 centimeters, and then we have the same charge on each one of those sides. So the first thing that we want to do is find the electric field at the center due to each charge. So the electric field here, we can just say the electric field is equal to EA plus EB plus, oops, that come out real well, plus EC plus ED. And we know that the electric field at A plus the electric field at B is the same as if I look at C, here's C, notice that it is in the opposite direction of A. So those are opposing each other. So I'm going to say that's really minus A. And then D really is opposite because we're using symmetry here. So D is opposite in charge and opposite in distance, so we're going to say that's minus EB. So if I go through and do that, I find out that my electric field is actually 0. Now we can do the same thing for the potential at the center, so we're going to say that the potential is equal to the sum of K times Q1 all over the distance. And so if we look, we have 4 charges that are exactly the same. So I'm going to say that's 4 times K times the charge, since they're all the same. And we're going to divide that by, and all of our distances are the same. So now we're going to go ahead and insert everything into our equation. So we're going to have 4 times K, which is 9 times 10 to the 9th. And our charges are all the same. They're all 9 times 10 to the negative 6th. Now we need to put in our R distance. So our R distance would be from the point here to here. So let's do that, but let's do it on a bigger scale and then just divide by 2. So what I'm going to do is, let's just do this in red. I'm going to go ahead and say I've got this big triangle here, and I have 2 on this side, I have 2 on this side. I want to know what is this side. Once I know that, I'm going to divide it by 2, and that should give me this right here. So let's go ahead and call this C, and we're going to say C is equal to the square root of, and we need to do 0.02 squared plus 0.02 squared. So if we do that, let's see what we get. And you get about 0.0283. So if we take 0.0283 and divide it by 2, we end up with our distance of 0.01415 or so. So this on the bottom is 0.01415. Now we can just go ahead and finish the problem. So we're going to go ahead and do our math. And you end up with 2.3 times 10 to the 7th volts, and that is your final answer. For number 20, which is the next one, very similar problem, but this one is definitely different because now I have a positive 9 microcoulomb charge, and then B, C, and D are all the same charge. So let's take a look at, and we're going to do the same thing. They want to know what's the electric field and the potential at the center. We have the electric field is equal to EA plus EB plus EC plus ED. And for this one, we're going to need to say the EA plus EB plus EC, and we can't do the opposite of A because this is not the same, even though it's in the opposite direction. However, we do know that D is just the opposite of B, so we can subtract EB from this one. And at that point, now we're going to need to plug some numbers in here. So this should be equal to K times the charge, absolute value of the charge on A, all over R squared, plus K times the charge on C, the absolute value of the charge on C, times R squared. And this should be toward C, and it's going towards C because remember we always go from the positive to the negative. At this point we can go ahead and put our numbers in, so let's factor out the K. The K here is just 9 times 10 to the 9th. And then the next thing we need to do is go ahead and look at QA plus QC. I think the other thing we can do is factor out the R squared on the bottom. And to do the distance, we're going to do the same thing we did last time. We'll just write it differently. We're going to put 0.02 squared plus 0.02 squared, and then underneath of the radical, we're going to divide it by 2. That will give us that distance that we wanted on the bottom. So now we've taken care of the K's, we've factored out the R's. Now we just need to do the charge on A plus the charge on C. So the charge on A is 9, and remember their absolute value, 9 times 10 to the negative 6th, and then, oops, I don't want to put parentheses there, 9 times 10 to the negative 6 plus 3 times 10 to the negative 6th, and the direction here is toward letter C. And so if you go through and do all your math, you should end up with 5.4 times 10 to the 8th newtons per coulomb, and your direction here is toward C. If we do the same thing for the potential at the center, something interesting happens. So V is equal to the sum of K times Q over R. And so now we have K over R, and we've got 3 charges that are Q. 3 times Q, because 3 times 3 would be 9, so we've got 3Q, that's this A charge, and then we're going to subtract Q, that's B charge, C charge, and D charge. 3 minus 3 is 0, so here the potential at the center is actually 0. And so now we are done with number 20. Let's go ahead and take a look at the very last problem. Last problem is number 24. Number 24, I have a spherical conductor. So it's kind of like our Van de Graaff generator. It's in a circle. Has a radius of 75 centimeters here, which is 0.75 meters, and has an electric field equal to 8.4 times 10 to the 5th volts per meter just outside of the surface. They want to know what's the electric potential just outside the surface, assuming potential is 0 far away from the conductor. So this is the electric field. They want us to find electric potential. We know that for a sphere, the electric potential is just equal to the electric field times the radius of the sphere. So this one is really pretty simple to do. It's just 8.4 times 10 to the 5th, and we multiply it times that 0.75 meters. Remember, everything is be in kilograms, meters, and seconds. And if that's correct, we end up with 6.3 times 10 to the 5th, and then our unit is a volt. And that is the end of the problem set.